Hello. I'll begin now. So today's topic is on pipelining slash data path. Um, yeah, this wasn't the most voted for option on the poll, but I think that given that we didn't have a pipelining question on the midterm and that the discussion for pipelining was grouped in with the midterm review, I think it's definitely worth going over. And therefore, actually, today's discussion of pipelining is actually just going to be a walkthrough of the discussion worksheet on pipelining. Because I think that actually has a nice comprehensive review of what pipelining is, how it works, how it affects clock rates and whatnot, hazard, stalling, forwarding, all the good stuff. It's all kind of covered in it. And I think that if you understand what's happening here, then you're in pretty good shape for the exam. Yeah. All right, so let's begin. All right, so if you're here to learn what the data path is, I'm going to have to unfortunately ask you to go refer to the lectures because I think the lectures do an excellent job of describing what different components of the data path are, what each phase is, um, and all this stuff put together. It has a really nice explanation, and I think me trying to summarize it wouldn't really be doing it any justice. What I'll briefly say though is that, currently right here, we're looking at the data path, and we can label it with the 5 stages that we know, right? This is instruction fetch. This is instruction decode. This is execute. This is memory. And this is write back. Yeah. Excuse me. Okay, so what's happening here is basically in this single cycle data path that we learned about, you could ignore all of these guys for now. We're going to come back to them just a little bit later, but what you should keep in mind is that this is actually a CPU. This is how it's designed, and this is all the hardware. And given at this point of the course, you should have done project 3 by now, which was designing your own CPU. So you should be very familiar with all these elements, right? So I'll just do a brief run through of what's happening, right? Like the components is simple, right? This is our PC, right? It's your normal program counter. It keeps track of the address of the code instruction that you're looking at. And obviously, each iteration of it, you will either move on to the next instruction, which is this PC plus 4, or you will go to some other address that's getting computed by your ALU. And we will come back to that. So for most instructions, it's just your PC that's getting updated to the next one. That PC gets fed into your instruction memory, which is, again, it's actually just normal memory. Like, there's actually just a normal mem. But the point is that we abstract away accessing different parts of memory. Because here in this stage, when we're doing IMEM, technically it's the same unit as this memory of DMEM. It's just a different part of the same piece of hardware. But these never really cross. Like your DMEM accesses should never really be touching anything that IMEM is accessing. So you feed it in there, and then outside of here is the actual instruction itself, right? And then as you can see here, we're also passing through the PC up there. Because that's the instruction fetch phase. Right? It's pretty straightforward. You take the PC, you feed it into memory, you feed it an address, and from there, you get out the instruction that you care about. Okay, so now that we're here, we do this decoding stage, which is basically break down the 32-bit instruction that you have and get the information that you care about. So as you can see here, we kind of break it up into these fields of, the 11th to the 7th bit, the 20th to the 24th bit, the 15th to the 19th bit, and they go into where they're expected to be. If you remember back when we talked about like instruction formats of RISC-V, right? There's a certain, given a RISC-V instruction, add RS1 or add RD RS1 RS2 or something like that, right? There's a certain way. There's actually like a deterministic and a set out way of translating these, instruction into 32 bits. And if you remember across all 5 instruction types, if you remember, there's an R type, an I type, an S type, an SB type, J type, and a UJ type instruction. I think. Or no, hold on. Sorry. I think it's just be this one. There are 5 or 6 types of instructions. I think there's only 5 types of instructions. Whatever, you can look at the green sheet for this. Regardless, across all these different types, one thing to keep in mind was that if this was our 32 bits, right, of the entire instruction, right, for some reason, if we ever had an RS1, RS1 was in the same position for all instructions that might ever need RS1. And the same thing happened for like RS2, for example. It would always be in the same couple bits. And we leverage that here when we're doing this, right? Because the point is, regardless if the instruction is using an RS1, an RS2, and an RD, if it is going to use it, we can expect the scripting bits for those to be in these positions. Okay, so you feed these 5 bits in here. Why do we need 5 bits? Well, because there's only 32 registers that we care about, and you only need 5 bits to specify 32 registers. And then from there, it will spit out the data that's in those registers. So this register file is just like an abstraction for saying you feed it what register you care about, and it will spit out for you the data on those registers. So this is RS1's data, and this is RS2's data. Okay. In addition, you can see that the entire instruction gets fed into here, which is the immediate generator. So if you look at the RISC-V instruction formats, you'll see that the immediate is always somewhere between the 7th and the 31st bit, right? So therefore, this is also an abstraction, right? This little immediate generator over here, because it basically takes the immediates that you care about, and depending on this signal right here, the immediate select, which is basically telling it what kind of instruction we're using, it will generate the appropriate immediate that we might use later. And then lastly, you'll notice that we feed the instruction bits into my entire control logic down here, this guy, right? And this control logic, if you remember from your project, was definitely, the biggest piece of heavy lifting you needed to do. Basically looked at the 32 bits that you had and took away some bits, and from there it was able to figure out, oh, that is this instruction, and based off of that, I should generate these control signals. Okay. So from the decode stage, we're left with the data at RS1, which is right here, the RS2 data, the immediate, and the instruction itself. And then as you can see here in the pipeline version, we also pass over PC, and we'll get to why that is the case a little bit later. The execute stage, just a couple things. Basically, everything is just executing around this ALU. Add, subtract, shift, multiply, divide, blah, blah, whatever you care about. And these little muxes here are choosing between the values that we care about. For like an R-type instruction, we're going to be using RS1 and RS2. For an I-type instruction, you'll be using an RS1 and an immediate. For a jump instruction, you'll be using the PC and the immediate, right? So different combinations of these 4 values will give you different things that you want. And from there, you're left with the ALU result and a couple other things. I noticed that we have RS2 that moves forward here. What else do we have? We also have this branch comparison, which is done, right? So if you have a branch instruction, BEQ, BLE, or BLT or whatever, it'll basically compute what that branch is going to be. And that will affect some stuff a little bit later. Okay, so that's what the execute stage does. And then from there, we'll deal with memory. So in the case of a load word or a store word instruction, your ALU will actually be outputting the address that you care about, and you will feed that into the DMEM. And if it's a load if it's a load instruction, it will just spit out the data in that memory. If it's a store word instruction, this obviously specifies the address that you want to store things at, and this is going to specify what you want to store. If you remember, the function of a store word instruction is like store word, like, I don't know. In this case, it would actually be RS2, some immediate RS1. And if you notice, what happens there is that we're actually feeding RS2 as the write data, right? And then we're adding RS1 plus the immediate to get the address that we care about. And it will store it in there. And sure, still technically when you're storing it, it will actually still spit out some memory here. But according to this mux over here, it actually will not continue through. Okay. And if you notice, the reason why we kind of piped it through here is because if we're passing the PC all the way over there, we can just add an extra +4 unit there. That way PC +4 will be able to pass through the entire thing, which will go into this mux. And then we also take the result of the ALU and we also make that equal to mux. The point is this mux right here is basically going to choose between different values that we eventually want to write back into my RD register. Oops, RD register. Okay, so obviously we're going to write PC +4 back to RD in the case of a branch instruction, or in the case of a jump instruction, right? If you remember, a jump instruction will jump to where you want to go, and it will also link PC +4 to your destination register. We also have the result of the ALU over here. That's like the most common one that you'll be writing back, an add instruction, R types, I types, blah, blah. You're writing the result of your arithmetic back to your register. And then lastly, the memory will be written back to a register in the case of any of the load instructions. So this mux will choose between all of those, and it will write it back over here. That's like a general overview of how the overall data path works. Quickly, just to talk about the control signals. So obviously there's a lot of decisions to be made on this data path. Each of these muxes needs to know what it needs to choose between. We have some of these things called like enable bits. We have more muxes. We have this ALU signal, write enable, this write back mux signal. Right, so what happens is you feed in the entire instruction into this control logic. It will break it down and it will generate all these signals. PC select will tell you, is the next instruction that I care about, is it just the one right below it, or is it some instruction that lives totally somewhere else? So obviously for most instructions, the next instruction that we care about is, the physical next instruction. But in the case of a branch or of a jump and certain branches, PC select should be 1, and I should choose the result of the ALU, which is the new address that I care about, the address of the new instruction that I'm going to. Register write enable is a signal that tells us whether or not we should be actually writing back to a register, right? So in the case of like an add instruction, right, then we should be writing back to a register. But in the case of like a store instruction or a branch instruction, I don't care about writing to a register, so therefore this would be a disabled bit. Immediate select is more of a general signal. It kind of just tells the immediate generator what kind of instruction we're dealing with, R type, I type, S type, blah, blah, blah. And then from there, it will just generate the appropriate, it will extract the appropriate bits right here, and from there, it will generate the respective immediate. Branch unsigned right here is a signal that goes inside of the branch comparator. Basically, it's telling the branch comparator whether its comparison should be an unsigned comparison or a signed comparison. And you should review your number rep to remember that, like, if it's an unsigned comparison, right, for unsigned numbers, all ones is much bigger than all zeros, right? But in a signed comparison, all ones is just straight up equal to -1, which is in this case less than 0, right? So obviously the choice of whether your comparison should be signed or unsigned is a pretty important one. I will come back to these guys. B select and A select are basically the two signals that are choosing what these muxes are going to be using, right? So in the case of like an add instruction, we want to choose RS1 and RS2. In the case of a jump instruction, I want to use PC and the immediate, right? Because I want to do PC plus my offset to figure out where I'm going, et cetera, et cetera, et cetera. ALU select, similar to immediate select, breaks down our signal. It breaks down the instruction and tells us what kind of ALU operation I want to be doing. For an add, I want to do an add. For a shift, I want to do a shift. For jumps and branches and loads and stores, I want those all to be adds, because usually for all of those, you're adding something to a memory address. Memory read write is a signal that just tells us whether or not we should be reading or writing from memory. Reading or writing from memory. Basically, for any instruction that is not a store, you should be reading from memory. Why? Well, if you read from memory, it will just spit something out on this wire right here. Right, so if it's a load, then that is actually what you care about. But let's say hypothetically you have an instruction that's not a load, this will still spit out a piece of memory. Okay, but since we don't care about it, this next signal, the WB select, will prevent that kind of garbage value from continuing on. So let's say hypothetically I have an add instruction. Very simple, right? If I have an add instruction, then obviously I should not be writing to memory because I'm not even interfacing with memory on an add instruction, right? So it will still spit out a value right here, but for an add instruction, what do I want to be writing back? Well, I want to be writing back the result of the ALU. So therefore this guy is just going to like not continue forward. All right, and that's what WB select does, and then we can move back there, and when we write back here, register write enable will tell us, are we allowed to write back to the register file? Okay, one thing I want to say, and this is also what you encountered in your project, was, okay, there's a special relationship. One thing to look at is that there are two signals that are actually taking in something as input, BREQ and BRLT. So these signals are basically the branch comparator is telling the control logic something. It's telling the control logic, look, this is a branch construction, and in this case, what you fed into me, it's equal, or one of them is less than the other one. RS1 is less than RS2. So why is this important? Why do we even care about the fact that the branch comparator feeds something into the control logic? Well, let me ask you a question. Let's say I have BEQ X0 X1 loop. Okay, let's say in this case, X0 is not equal to, actually, let's a little bit clearer now. X0 is not equal to X1. Well, in that case, oh, it's going to be lagging a little bit. Okay, cool. Okay, yeah. It's not equal to X1. Well, in that case, let me ask you a question. Should we branch? No, we should not branch. Okay, but let's say hypothetically I have BEQ X0 X0 loop. Well, in that case, I should branch. Okay, so what is, in hardware, what is the difference between branching and not branching? It all has to do with PC select. If I should branch, then PC select should be 1. If I should not branch, then PC select should be 0. So in this case, PC select should be equal to 0, and in this case, PC select should be equal to 1. So therefore, these guys are intimately connected to PC select. And you implemented this in your project 3. You said, look, if it's a branch equal instruction and the BREQ signal is on, then that means that I should branch. So therefore, the next PC should be the address of the instruction that I'm branching to. If it's a BEQ instruction and branch equal is off, then that means that I should not take the branch. So therefore, I should just go to the next instruction in PC plus 4. So that's this relationship between both of these. Okay. Now, one thing, just forecast that we're going to talk about in a bit, is that obviously, in the case of a pipeline, this actually doesn't show up until much later on, until stage 3 of the pipeline. But the problem is PC select is all the way back into stage 1. So it's as if we're learning about whether we should branch or not much, much later. This is like known as a control hazard. But we will come back to that. Okay, so that's the single cycle data path. So now let's talk about pipelining. Pipelining tends to confuse a lot of people, and I think it kind of like seems very daunting, but it's very straightforward. All pipelining is throwing registers between stages. That's it. That's all we did. So I'm actually going to erase all of these notes that I made right now, just so that I can make everything a little bit cleaner. Okay, so all we did, if you notice, is every wire that, first of all we did was we just kind of split it up into the 5 stages. And then every wire that crossed these stages, we just threw a register in between them. That's it. That's all it is. There was no like special artsy way or figuring out what's happening here. We literally just threw this between every single one. That's all. That's all it was. There, immediate is passing through. The instruction is passing through there. The PC is passing through. Every wire that's crossing one of these red lines, you gotta pipeline it. Okay, that's it. That's all pipelining was. Okay, and intuitively how you can view it, pipelining is like if you're ever driving on a freeway, let's say you're at like a toll, like you're at like a gate, one of those things, right? And the point is that you have to stop and you're not allowed to continue until what? Until the gate is lifted. So you can consider pipelining here to be there are this many like toll booths. So between instruction fetch and instruction decode, we basically have 2 toll booths. And you consider like cars are just driving down. Right, and the key with all of this is that all the gates open at the same time. So therefore, even though PC might get there first, it has to wait until the instruction gets to its register before we can open both of those gates. Because all the gates open at the same exact time. Okay, the same thing happens for this stage and blah, blah, blah. Okay, so think of it like a gate. Everything approaches it. Once everything is ready at all these gates, then you could tick your clock, open everything, and allow things to flow through. That is all pipelining does. Okay, and the benefit to this is that now I could tick my clock faster. Because instead of having to wait, so first of all, each of these is like a clock, right? So I'll be like ticking my PC and I'll be ticking my register file and ticking my memory at the same time. And the point is, every time I tick my clock, in the single cycle case, I would get my PC, and then as I went through earlier, everything would just propagate through the entire data path. But now that I have a pipeline, what it means is that everything doesn't propagate through the entire data path. The PC will travel, but then it'll stop. And it will go here and it will stop. Everything will stop right there. And then you'll just tick it again. And now when you tick it again, whichever guys were here will pass through across there, and then a new PC will pass this guy there. And on the next tick, these guys will move across, and the next tick, these guys will move across, and et cetera, et cetera, et cetera. Right, so the idea is now I could just tick my clock much, much faster because I don't have to wait for all of this work to happen. And the benefit to this is that at any one point in time, I could actually have 5 different instructions executing on the data path at one time. Okay, I think in lecture, Dan uses kind of laundry analogy of like when you want to do your laundry, let's say you have like 2 batches of laundry. Okay, which one's more efficient? Like doing one in the entire system of like taking it down to the laundry room, throwing it in the washer, waiting for it to be finished, then throwing it into the dryer, then folding it, and then doing the next load. Or instead, why don't you put one load in the washer, okay, when that load's done, put it into the dryer, and then bring the next load into the washer, and then you just kind of like do this kind of steps. The same thing is happening here. At any one time, I will have 5 different instructions. Each one is executing in each phase at the same exact time. And the good news is that everything's modular. There's very little stages that are actually dependent on each other. So this is totally possible. And this is why if you look, we actually have the instruction that's getting fed into the control logic at every single stage of our pipeline. Because obviously the control signals for that stage are dependent on the instruction executing in that stage at that time. Okay. Now, one thing to keep in mind is that if you look in the previous like worksheets and whatnot, you'll actually notice that what we did was we actually took PC plus 4 here and we kind of like pipelined that there. But just to save time and energy, all we did here was we just kind of like, or actually we pushed PC plus 4 through there, and that's actually how we did stuff earlier. But the thing is that this stage, the execute stage, actually needs the PC, so therefore we're kind of like utilizing the PC in two ways. We're pushing the PC across on all these stages, and then when we need to use it, we will use the PC. And then later on, when I need to compute PC plus 4, I have this extra plus 4 there. Okay, so that was like a pipelining specific thing that we did. In addition, as you might notice, we decided to move the register here for the write back after the mux rather than before. Not super important, but something to keep in mind. So that's the general gist of pipelining. Let me see if there's any questions. So for whatever instruction that we are running, do we always go to memory? Yes. Yes, we actually do always go to memory. This is actually something called asynchronous. It's an asynchronous memory access, which means that regardless of what's happening on our CPU, like stuff is still happening, there's like some other guy, like some other worker who's going to memory and doing stuff. Does that mess with the content of our cache? Technically, yes, it does mess with the content of our cache, but we won't worry about that for now. All right. Well, a lot of cache questions recently. It would mess with it, but I guess what you could assume is that since we actually don't care about what's coming back, there could be extra logic in place that can prevent this from actually going back to memory. Okay. Yeah. Okay. Cool. So, okay, yeah. I think that's all I'm gonna say, like lecture-wise for this. So, okay, let's jump into the worksheet itself here. So, actually, is there anything else I want to say? Both stages. Okay. Yes. We'll talk about hazards a little bit later. Yeah, this is pretty much all I want to say. Hopefully this should all be like pretty conceptual review. I think the CPU project pretty like, kind of ingrained this into your mind, what the point of all this is. Okay, so now let's go to the worksheet. In order to pipeline, we add registers between the 5 data path stages, label each of the 5 stages. Okay, we already did this already. IF, ID, execute, memory, write back. What is the purpose of the new registers? I'm not going to write this down because I just want to like save time here. The purpose of the new registers is to pipeline. That's literally the point of it. And it basically allows us to clock things faster. Okay, it's basically what I said earlier. Okay, we throw stuff in any circuit. It doesn't need to be the CPU. I think there was a lab on just like normal like timing circuits. You can just throw registers between things because registers are controlling how fast you can tick your clocks. All of these registers are clocked here, by the way. Okay, why do we add +4 to the PC again in the memory stage? I also went over this actually. It's because we pass the PC through because we're going to need it in the execute stage over here. However, we also need PC +4 over there, so we just add the extra +4 unit there. So without needing to also pass in an extra value, which would require another register there, right? We're trying to minimize the amount of hardware that we're using. Why do we need to save the instruction in a register multiple times? This was also gone over. This is because the control logic for one instruction does not apply to all the instructions in the pipeline. At any instance in the pipeline, we have 5 separate instructions executing at the same exact time. And the control signals for each of those are very different. So therefore, you can consider that this control logic is also split up. And that's a totally reasonable thing to do. That is not a problem at all to have it take in 5 different instructions and compute the appropriate control signals for that instruction. So we have to feed the instruction into it every single time. All right, great. Okay, now we have performance analysis. Sure, I'll go over it. Why not? I think it's like it's a nice way of showing what the good parts of this are. I'm just not going to do all like the annoying math. I'll just leave that as an exercise to the reader. So, with the delays provided above for each of the data path components, what would be the fastest possible clock time for a single cycle data path? Okay, so when we're looking for the fastest possible clock time, remember, we're looking for the slowest instruction. Because this means the fastest we can possibly tick our clock, right, is limited by whoever the slowest guy is. So if we look, you'll kind of need to look about it for a bit, but you'll think about, and you should think about, which instruction utilizes the most components in a single cycle data path. It turns out it's actually the load word instruction who does. Why? Well, load word utilizes the PC, and it has to fetch something from memory, and it has to deal with a register file, and it has to generate the immediate It does the ALU. It does not actually need the branch comparator. It does read from memory, and it uses uses this mux, and it writes back. It pretty much is using all 5 stages. On the other hand, there are some instructions that don't use all 5 stages. For example, a store word instruction. A store word instruction does not use this stage, the write back stage, right? Add instructions, R type instructions, do not use this stage, right? So obviously there's certain instructions that don't use everything. Okay, so the load word instruction uses all 5 stages, and if we look, the fastest possible clock time would be, it would be the time for so the time equals, we want the PC clock to queue first. That's the first thing that happens here is the PC, and then we go to the instruction memory. So we'll do register clock to queue, okay, and then plus. Next we go to the instruction memory, so that would be a memory read right there. So plus mem read. Plus, well, next we go to the decode stage. We need to, in parallel, go to the register file and the immediate generator. So if there's any 2 hardware components that are happening in parallel, you just take whichever one is slower. So in this case, the register file takes 150 picoseconds to read, whereas the immediate generator actually is not even on here, so therefore we're going to assume it's instantaneous. So therefore it's going to be a rec file read. Okay, then plus, now we're in our execute stage. So again, you just have to kind of enumerate all the different paths in the stage. So one path is going through that mux and the ALU, another path is going through this mux and the ALU, one path is going through the branch comparator, but since we don't care about the branch comparator, we're just going to ignore it. So therefore, the time for this is the time to get through this mux, and then the time to get through the ALU. So therefore, plus the mux time, plus the ALU time, and now we're in the memory stage. So since it's a load word instruction, we want to go to data memory, and we're going to be doing a memory read, and then plus this mux right here. So therefore, it's going to be a memory read. So memory read plus another mux. And then the last thing that we need to do is we actually need to write back the value to here. So in order to write back to the register file, a register file is actually just an abstraction for 32 registers. And whenever we want to write to a register, what do we need to wait for? The setup time. So therefore, the last thing that's going to be added here is the register setup time. Okay, cool. If we look, so we utilize clock to queue, we use setup, mux, no branch comparator, which makes sense because the load doesn't use the branch comparison. ALU, memory read, memory write, this is a load word, so we don't care about writing to memory. Reg file read, reg file setup. Okay. If you want a more thorough analysis of this, you could actually look at the discussion worksheet for the single cycle data path where we actually enumerate all the different instruction types. So we go through R, I, S, SB, J, UJ, and we actually, we go through all of them and we compute how much time they all take. It turns out, in general, whoops. It turns out that, oh, I apologize. Give me 1 sec. Is that? In general, all instructions of the same instruction type, there we go. All instructions of the same instruction type take the same amount of time. All right, cool. So I'm not actually going to do this math, but this gives you the time for one period, for one clock cycle. You can do 1 divided by this to get the frequency. What the? Yeah. Let me check. Let me see if there's any questions about this for now. Oh, okay. All right, wonderful. Okay, hopefully this does not go out again. Okay. What is the fastest possible clock time for a pipeline data path? So for this case, what we need to do is we actually just, well, now instead of between each clock tick, it's not the entire data path that we're going through. Between each clock tick, it's whichever stage takes the longest. So now we can just look at each stage, right? So let's first look at the instruction fetch stage. So this guy, when we tick the clock in the instruction fetch, what do we have? Well, we start off with the PC here. right? And then we have to do this memory read. And then one thing to keep in mind is that since there's registers between each stage, we also need to be concerned with the setup time of each of these registers. So therefore, the time for the instruction fetch stage is going to be a clock to queue plus a mem read, right, to fetch the instruction, plus the setup time. Now, at the same time, you could actually also include this +4 and this mux, but I think if we look at it, the time that it takes for the mem read actually trumps the time that it takes to go through that mux. As like an overarching theme, whenever you're looking at these pipelining like circuits, you basically need to enumerate all the different possible paths. So there's just 2 here. Actually, there's 3. This is path number 1. This is path number 2. Oh, whoops. This is path number 2. And this is path number 3. And so this guy, which goes through IMEM, is the longest path. Okay, now for the instruction decode stage, let's look at all the different paths. So these 3 guys are all kind of going through the same thing. It's basically a register file read. At the same time, we have the immediate generation. If you remember from earlier, though, it turns out this, we're assuming, takes no time whatsoever. So therefore, the instruction decode stage just takes, 1, the clock to queue of taking, the value from this stage going into that stage. So it's clock to queue, plus an RF read, rec file read, plus the setup time again. Because we're concerned about this clock to queue of getting the value from the previous stage to the current stage, and then we're worried about how long it takes for us to set up before we can write to the registers of the next stage. Seems I'm lagging a bit again. This is what I get for using free software. Okay, wonderful. All right, next. Why are you lagging so much? I apologize. Give me one moment. Let me figure out why this is taking so long. All right, well, I'm going to disconnect and reconnect real quick. Oh, okay, cool, we're good. Wonderful. Okay, great, awesome. All right, so that's what we have for the ID stage. The execute stage is where we have a lot more paths, actually. So, for the execute stage, we have, this is one path. That's obviously going to be the fastest one. We have this path, which is going through a mux and then going through the ALU. This is a similar path, mux to ALU. This is a similar path, mux to ALU. This is a path of branch comparison. Yeah, so those are basically like our different paths. One thing to keep in mind is that when we're doing this, as you can see, I'm not actually enumerating what kind of instruction we care about. And that's because since at any point in time, any instruction could be in any of these stages, you have to assume that like anything could be done here. Okay, so assume that it is the worst case. First of all, one thing to keep in mind is that the entire data path needs to be clocked at the same time. So therefore, your pipeline is only as fast as the slowest instruction in one of the stages. So therefore, we're going to look at one of the stages and say, what is the worst possible situation in this stage? That would be our slowest time. Okay. So we're going to choose between the branch comparison versus the ALU time. So therefore, it's going to be the max of, or actually, I'll just do it this way. It would be the, whoops, I want to erase, there we go. So execute would be clock to queue plus the max of the ALU plus the setup time and the branch comparator. Yeah, branch comparator. Okay, so whichever one is slowest out of those guys, That would be kind of our bottleneck on the entire one. Okay, and here we have the memory stage. So for mem, we have a couple different paths here, right? We have one here. That's just this mux because we assume that that's negligible. This assumption is just given by the fact that nowhere in the problem does it tell us how much time this takes. This is like me saying it's negligible. We have one case where we have like a load instruction that will read and then go through the mux. Then we have a case where we need to write and then go to the mux. So therefore, it would be clock to queue plus the max of a read or a write. Actually, hold on. It would actually be the max of reading plus going through the mux plus setting up to write it back, or just simply writing. Right? Because if we write to something, then we don't care about what's getting outputted here and what's going to get put into that register, so we don't need to worry about that. Okay, and then our write back stage is simply just the clock to queue of this guy plus the setup time of having to write to this guy plus RF setup. Great, so now that we have all of these values, let's look at which one is the slowest. So the fastest possible clock time is whichever one of these stages will take the longest. So for the sake of speed, I'm just gonna like, actually, no, I'll be fair. I will not look up the answer. Just do it myself. Okay, so I couldn't do this on the same page. Okay, clock to queue is 30 plus a memory read, which is 250, plus the setup time, which is 20. So this equals 300 total. The instruction decode stage is clock to queue, which is another 30, plus a register file read, which is 150, plus the setup time, which is 20. This is 200. Okay, execute is clock to queue, plus the maximum of the ALU, which is 200, plus the setup time, 20, versus the branch comparison, which is only 75. So obviously that's 30 plus the ALU and the setup time together, which is 220, which equals 250 total. Okay, and then from here at the memory stage, we have clock to queue, which is 30, plus the max of reading from memory, which takes 250, plus the mux, which is another 25, plus the setup time, which is another 20, versus a memory write, which is 200. So that's equal to 30 plus, obviously the reading takes much longer, so it'd be 250 plus 25 plus 20, which is 295. So this gives us a total time of 325. And then lastly, the write back stage is just clock to queue plus the register file setup, which is 20, which is just 50. So obviously, the memory is our bottleneck stage. It takes 325 picoseconds. There you go. Mem with 325 picoseconds. Right, okay. I actually will double check my math just to make sure that I didn't do anything wrong. Where am I looking? Oh, here. All right. Here we go. So, perfect. Yeah, 325 picoseconds. All right. Amazing. Okay, cool. Then what is the speed up from the single cycle data path to the pipeline data path? Okay, so I'll just tell you right now that the answer to this problem was 950 picoseconds. So for the single cycle data path, it actually took 950 picoseconds. For the pipeline data path, we can actually clock once every 325 picoseconds. So the speed up was, you can do 950 divided by 325, right? Because of that, it took that many times as slow. And that actually took us a 2.9 times speed up. Okay, so clearly, we have a 5-stage pipeline. However, I'm only able to get a factor of 3 by speed up. Why is this the case? Well, it's because there's a lot of overhead. Right? If you notice, in every single one of these computations, I had to take into account clock to queue and the setup time. This kind of adds up over time, right? So therefore, there's some overhead to doing pipelining, and that's why we won't get that perfect 5 times speed up. Okay, so that's it for the clocking questions. Let's see, any questions about this? I will wait a bit. Wow. Is this the number of people who are actually watching? Watching one. Wow. Shout out to you. You're in this like one-on-one tutoring session. Amazing. That's what you get like for starting studying early, I guess. Okay. All right. It seems like there's no questions, so I'm gonna continue on. All right. Next question: hazards. Okay, so this is actually I think like the meat of like pipelining, and basically what it comes down to is this is a wonderful idea that we can actually speed up what's happening. This is instruction level parallelism here. Like this is kind of like this is your first introduction to parallelism because you're saying that at any one time I can have all of these things happening at the same time. I'm literally parallelizing my stuff, and I can run 5 instructions in parallel, and that's wonderful. And I was able to get this 3 times speed up in this case. However, the truth is that not everything is that nice, right? Like doing this actually introduces some problems. The first problem that we're going to talk about is something called a structural hazard. A structural hazard basically means that the CPU is one piece of hardware. And there are actually certain cases where multiple stages are actually trying to access the same piece of hardware. Primarily, we can see this in 2 places. Excuse me. One is in this register file. Okay, why is this the case? This is the case because both the instruction decode stage and the write back stage are both utilizing the register file, right? However, if you look at it, this is actually not even a problem. It's already been solved in the design of the CPU. Okay, if you think about it, it's saying like, oh, 2 people are attempting to access the same thing at the same exact time. That could be a problem, right? But the good news is the way that this register file was designed basically said that reading and writing actually are done on 2 completely different sets of wires. Okay, so therefore it's not actually a problem that they're both trying to access the same piece of hardware. Okay, now your inclination might be, well, that's great that they're both accessing the same piece of hardware, but what if it's the case that while one instruction is in instruction decode attempting to read from something, and one instruction is in write back attempting to write back? What if they're dealing with the literal physically exact same register? What happens? Well, we would actually need to tell you what happens. So in some designs, not all, of CPUs, they do something called double pumping. And double pumping is a fancy way of saying read then write. Or sorry, it's the complete opposite. Whoops. Write then read. And we'll get to this like in a little bit when we talk about data hazards, but it's basically saying if 2 instructions are attempting to access the actual physical same register at the same exact time, if you want to get the behavior that you actually expect, you should let the write back write to it first, and then let the instruction decode read to it second. And when this is done, it's saying like, oh, you can write to it in the first half of the clock cycle, and you will read from it in the second half of the clock cycle. This is not an assumption you can make all the time. Be aware of this, all right? We have to tell you, assume that you have this special kind of register file that allows for this kind of stuff. Now, why is it the case that you want to write then read? Well, that's because the instruction that's in the write back stage is the earlier instruction, right? So obviously, if you have an instruction that wrote up here and you have one that's reading down here, obviously you want the result that's getting written back here to be, updated first before you attempt to read anything down here. Okay? So the other instance of a structural hazard actually has to do with memory. So as you can see here, in 2 stages of the instruction fetch and in memory, we're actually accessing memory at the same exact time. But again, this has also been solved by the design of our data path. Because we're saying that by abstracting away memory into a data portion and an instruction portion, you don't need to even concern yourself with the fact that they're both accessing the same piece of hardware. Because they're accessing 2 independent parts of that same piece of hardware. So they'll never crisscross, and that shouldn't be an issue whatsoever. Yeah. One like cool caveat to this, just to mention it, is that when we studied caches, we always talked about data caches. Well, this is also accessing memory, so it turns out you also have an instruction cache as well. We never really get into it, but it functions the exact same way as a data cache. And if you ever did loop unrolling in your project, or if you remember going over that in the lab or lecture, it turns out loop unrolling works because of eliminating certain kinds of hazards. However, the reasoning why you can't just loop unroll forever actually has to do with your hit rate of your instruction cache, and how if you unroll your loop too much, you're actually avoiding any kind of spatial locality in the physical code that you're executing. It's kind of a big brain topic, and you just kind of think of it at a high level, but the point is, if you write too much physical code, it's like traversing it. Like there's actually a locality to how you could be executing code as well. So if you unroll too much, you're completely getting rid of any kind of spatial locality in the code that you're executing. Or temporal. I guess like they both work in this case. Okay, so that's it for a structural hazard. Let's see if I measure anything. Yep. Read and write ports, double pumping, cool. Memory is access, having separate instruction memory and data memory solve this hazard. Perfect. Okay. Yeah, big picture, you could always solve structural hazards by adding more hardware. Okay. So the point is you'll never actually see a structural hazard come up in this design of the data path. Okay, next we have a data hazard. And data hazards, I think, are best illustrated by an example. Okay, so let's look here. So we're not going to get to forwarding yet. Let's just look at these three pieces of code. This add I, T0, this and. Okay, so what's the problem here? Okay, so this is kind of like these diagrams of like how we look at pipelining stuff when we look at hazards. It's basically saying that in cycle 1, instruction 1 is in the IF stage. In cycle 2, instruction 1 is now in the ID stage, and this guy is now in the IF stage. Right, so at any one time, these are the placements of the instructions at different stages. If you can see, it makes sense, right? It takes 5 cycles for instruction 1 to get through all of its stages. And then after that, it'll take another 5 for this guy, etc., etc. All right, so, okay, what do we see what the problem is here? So there's actually a problem with how this code is working. Okay, this is an add instruction, an add-I instruction, and it's reading from T0, it's reading from A0, so it does the reads in this stage. Right? It's literally reading from the register file the values of T0 and A0 in the ID stage, instruction decode. Okay, and it uses them in the execute phase. However, we do not get the result that we put into T0 until when? Until the end of the WB stage. Right? Here is when we're actually doing the writing. Okay, what is the problem here? The problem here is that I am writing to T0 all the way down here in cycle 5. However, this AND instruction is going to attempt to read from T0 in what cycle? In cycle 3. Okay, so clearly what happened? Like, what was the problem here? So the problem here was that T0 was not updated in time. If this was a single cycle data path, and we did not care about pipelining, what can we assume? Well, we could assume that this guy would complete all the way to the end, and everything would be perfect, and then we would start this guy. So therefore, the T0 that it would read here would be correct. But when we have a pipelining, I'm attempting to read T0 too early before it's been updated all the way back here. This is known as a data hazard. Okay? Things are happening too fast, and I'm being a little too hasty in when I want to read stuff. So there's a couple ways of solving this problem. And if you look, actually, just one more thing to mention, this also actually affects instruction 3 as well, because it also attempts to read T0, right? So T0 isn't ready until cycle 5, but this guy attempts to read it in cycle 4, right? So it's actually affecting everything. So in this case, given no solution, these guys would actually be executing the wrong thing, because they would be using an outdated value of T0. Excuse me. Yeah, so how do we solve this? There are 2 common solutions to solving this. One of them is called forwarding. Forwarding is basically a way of saying, instead of waiting until the very end to write back the value, take the value once it's computed and move it to where it needs to be. So what does this mean? This means that, okay, T0 is ready when? It's ready at the end of the execute stage, right? As in, I'm taking A0, I'm subtracting it by 1, and that value is here. It's on this wire. And it's ready. Now, it's going to take 2 more cycles for it to actually reach and get written back to the register. But the point is, it's ready there. So then what could I do to solve this? Well, I could say it's ready here, and I need it when? When is the latest instruction 2 might need it? instruction 2 needs this guy right before it enters here. Or I guess you can say right here, right? So therefore, what I can say is I will forward the value here. Okay, let me make a cleaner arrow. I'll use a different color for this. Okay, the point is you take the value when it's ready there, and you will forward it there. Okay, you take the value of A0 minus 1. That is what is going to be inside of T0. But I need it immediately, right before I execute this instruction. So therefore, you'll take the value and move it there. And the same thing could happen here. I will take that value, and I will simply forward it there. Okay, I guess I can draw the arrow like another way. There, I could forward it there. Okay, so this is what's known as forwarding. You literally are wiring the value from when you need it to where it needs to go. Now, as like an addendum, how is this actually implemented in hardware? Well, there's some extra logic involved, but it's basically like an extra little wire that will go up here that will take the result of the ALU, and it will actually kind of loop back, and it will mux it in there. And there will be extra logic here that will keep track of when I should actually be doing this or not. Okay, and there might be like a register involved here that will keep track of it. I'm not going to get into like the intricacies of it, but like that's just how it's implemented at a high level. You take the value what it is, you add an extra value, you bring it back, and you say, look, if there's a data hazard between the instruction that just went through the execute stage and the instruction that's about to go through the execute stage, then push that value back. Okay, override what was in RS1. Okay, so that's how you do forwarding. Is that straightforward enough? Is there a question? No? Okay. So that's how forwarding would work here. Imagine you're a hardware designer working on a CPU's forwarding logic. How many instructions after the add-I instruction could be affected by data hazards created by this add-I instruction? It's a wonderful question. It's basically saying I have this add-I T0 something. How many instructions past that could be affected by a possible data hazard here? Well, we saw that at least these two have to be affected, right? So if I look, the next instruction, which in this case was what, an AND instruction, and something T0. This is an SLTIU instruction, something T0, right? And these both were problems. However, let's say I add a third instruction. Let's say I'll add another add instruction. And this guy will do, I don't know, T5, T0, T1. So it would look like this. Its IF would begin there, ID, execute, mem, WB. So would this still be a problem? Would there still be a data hazard between these two instructions? Let's look. T0, it gets written back here, okay? However, I need it at the beginning of the instruction decode stage. So this answer depends on our assumption about the double pumping. Okay, it is ready at the end of the write back stage. However, I need it in the beginning of the instruction decode stage. So if double pumping is possible, I guess actually I'll write a more informative term. If it's a write then read, then there is no data hazard for instruction 4. However, else there will be a data hazard. Right? If these two guys are aligned, WB and this ID stage right here, if they're aligned, it all depends on which one is happening first. Am I reading from T0 first, or am I writing to T0 first? If I'm reading from T0 first, then the correct value will not be written back yet. So therefore, it will still be a data hazard. However, if double pumping is enabled, if the write occurs before the read, if write then read, then there will no longer be a data hazard. Okay, so this, where am I looking? Here. It depends. And the answer for Y is basically this right here. Okay, so therefore, if double pumping, then we 3 instructions would be affected. If no double pumping, then only 2 instructions would be affected. Okay. Cool. All right. Wonderful. So then there's another way of solving this. Actually, there's not another way. However, it turns out forwarding is not the solution to all of our problems. So let's look at why that's the case. Well, let's look at more code. So, it's kind of good practice for these, just to be able to kind of look at code and kind of see where there might be data hazards. So usually that practice evolves to like, okay, well, I'm writing to S0 there. Am I ever reading from S0? No, so there's really won't be a data hazard there. I'm writing to T0 and I'm reading to it in the next stage. That probably most definitely is a data hazard. I'm writing to T1 here and I'm reading to it in the next stage. That's also a data hazard. It's even lagging a bit. Okay, cool. So let's look at the one between 2 and 3, the T0 one. Okay. And also, one thing to mention is that, like we said earlier, the data hazard affects 2 or 3 instructions below it. If this guy was a T0, then that would also be a data hazard, but it's not. So the problem here is that in instruction 2, I have my value ready here, and I need it here, so that's good. We could actually forward this, and everything's fine. So this guy's okay. I could forward him, and I could fix that problem. Right, T0 is ready there. I could forward him there. Okay, now what about T1? For a load word instruction, when is T1 ready by? Well, I need it, obviously, here. When I need T1. However, when is it ready? It's ready at the end of the mem stage, right? Because I'm loading the word from memory. So therefore, forwarding cannot solve the problem. I cannot draw an arrow into the past. I can't take something from the end of the mem stage and push it into the beginning of the execute stage. That wouldn't make any sense whatsoever. Right? Like, if we look back here, like, there's no way I can take a wire here. Like, if I tick the clock, right, the execute stage would begin and the mem stage would begin at the same time. This is saying take from me something here and pull it all the way back there at the very end. It just wouldn't make any sense. It just wouldn't work. Okay, so therefore what would happen is, oh, sorry, I just noticed that my diagram here is a little bit incorrect. I would actually, if I want to implement forwarding, I would actually move the logic here. I would say, look, take the result of the ALU, move it into the previous stage, and overwrite what is on RS1. That way, when you tick the clock next, the correct value would get pushed through there. Yeah, and this would be logic here. Logic. Okay. Anyway, so sorry, that was a little bit of a tangent, but the point is that I actually cannot forward this value. Basically, forwarding does not solve this data hazard for this load word instruction. It just straight up does not. So what's the solution? The solution is to do something called stalling. Okay, so forwarding cannot fix. Okay, so the way that you solve the hazard is you simply delay, or as you saw in your CPU project, you stall the load word, or you stall the add instruction for a cycle. If I stall the add instruction for a cycle, I'm gonna, oh, sorry about this. Yeah, let me rearrange this. So I need T1 there, and T1's ready there. Okay, if I stall for a cycle, so if I stall, then that corresponds to essentially moving everything down by one stage. Okay, and if I move everything down by one stage, well, now what happens? Well, now I need it there, right? And it's ready back there. So now I could actually forward it. Okay, so stalling is equivalent of inserting a no-op. So that means that in between there, I would have a no-op instruction. Okay, so therefore instruction 4 would become a no-op, and this guy would become instruction 5. All right. So clearly the logic for data hazards is a little bit more complex, but it's not like that. Like, it's not too unreasonable to think about the logic like conceptually through your mind, right? What did we say? We said, look, if, like in a forwarding case, if a future instruction relies on, if a future instructions register that we're attempting to read from is relying on something that's getting written to in the previous instruction, that's a data hazard. Do some logic to bring it back and overwrite the appropriate value. You could add some extra logic if this is a case, and the instruction that I'm previously waiting on is like a load word instruction, right, then I know that the result won't come until very later, therefore mux in your no op. Okay, so this is all just kind of extra if conditionals you can put here. Okay, so that's a solution. In the case where you cannot afford, you need to stall and you need to insert no ops to solve some of the data hazards. This is, I think when I took my midterm two, the year that I took this class, we had a question. This is fall 2017, by the way, if you want to take it. It was a really, really long question. It was pretty tough. It basically said, here's a piece of code. There are all these hazards. Rewrite the code with enough no ops, assuming forwarding works, to make it work correctly. Then you could ask, okay, assume forwarding does not work. If forwarding is not an option, then your only option is to stall. So therefore, you're going to have to insert no ops everywhere in that case. But you just want all these things to line up correctly. All right. Next question is, say you're the compiler and can reorder instructions to minimize data hazards while guaranteeing the same output. I think it's kind of like a beautiful question because this is basically saying like, this kind of like shows off how smart compilers are. Because compilers will actually do a lot of this logic for you before you even get down to the hardware level to try to minimize as many data hazards as possible. So our problem here was what? Our problem was here. Basically, we want an instruction to go in between the load word and the add to function as the stall. If I put in a no up there, I'm kind of wasting an entire cycle. So instead, what could I do? I could actually move instruction 1 between 3 and 4. And that would actually solve our problem. S0 does not rely on anything. This instruction is literally living in its own world, and none of these guys depend on it whatsoever. So I could actually move that instruction in between instructions 3 and 4, and that will effectively delay the add instruction by 1, which allows everything to line up. That way forwarding could still work. Okay? Cool? That's kind of a cool problem. This is the last thing we're going to talk about with data hazards. It's basically like the logic inside. And I kind of talked about it before, right? You have access to all of these signals, RS1, RS2, register write enable, RD for 2 different instructions. Given all of this, how would you implement logic to tell us whether I should forward or not? And we wrote it down here, right? If in the next instruction, you're attempting to read from a register that you're writing to in the previous guy, either RS1 or RS2, and you're writing to that register, then that's a data hazard. Pretty straightforward. And you saw that here, right? The way that we looked at it, you simply look, okay, this guy is writing to T0. In the next guy, I'm simply reading from the same guy. That's a data hazard. Same thing here. Oh, I'm reading from this guy, data hazard. Right? So that's how, that's where some of the logic that would get implemented here would be. You could do like some equality checks. All the values are actually here. RS1 is here. You can keep more registers. Point is, everything can get more complex, but that's all possible. And it all makes our stuff run faster. So those are what data hazards are. The things to keep in mind, forwarding when you can. Things depend on if you have like read then write registers or write then read registers. This whole double pumping issue that affects how many data hazards you might have. When forwarding fails, how you have to go to stalling. When you don't even have forwarding available, you would stall. How you could reorder instructions. That way you can kind of like minimize the number of no ops that you might have, but still get the same behavior. These are all the big ideas that would get tested on Xeya. All right, before we get to the last topic, which is control hazards, I will see if there's any questions. Sorry, can you explain the structural hazard again? Sure, yeah, of course. So structural hazards. Okay, first of all, I think double pumping makes more sense for the sake of a data hazard rather than a structural hazard. A structural hazard, basically at a high level, is saying in a pipeline, ignore the whole wiring situation. It says like in a pipeline, you'll have multiple stages which utilize the same pieces of hardware, right? The register file is utilized by 2 stages, and memory is utilized by 2 stages. At a high level, this might seem like a problem. Like if you consider just kind of be like one resource that your 2 guys are attempting to access at the same time, you got to have some way of mediating who's going to get it first and who's going to get it second, right? It's impossible to give it to both guys. So the solution here, which was a pretty naive solution, was just simply split up your register file. Why does it need to be the case that 2 stages need to access the exact same resource? In reality, they don't. The instruction decode stage only needs to read from registers, whereas the write-back stage only needs to write to registers. So by separating that process in the register file, we have solved that structural hazard. The second structural hazard was memory. We were just saying that the instruction fetch stage and the memory stage are both reading from memory, right? And that might be weird if they attempt to read from it at the exact same time. Well, the solution to that is, well, it's kind of straightforward that if we separate instruction memory and data memory into two different portions, we'll never have this issue because they'll never collide and attempt to access the same piece of memory or write to the same piece of memory. Data memory only deals with, like, static, heap, and stack, whereas instruction memory only deals with the code portion. So they'll never, like, hit the same portions of memory. The whole idea of double pumping was, if I have this register file, it's great that I can separate the reading and the writing. However, what about the edge case where I'm reading and writing to the same exact register at the same exact time? Then what happens? Well, that all depends on the on the order in which it happens, right? Obviously, one of them needs to write to it first, and one of them needs to read to it, or one of them needs to read. One of the operations needs to go first. It either reads first or it writes first. Right. So in the case of where it writes first, well, it should make sense that if you actually want the behavior that you're looking for, it should write first. The instruction that's in the write back stage is the earlier instruction because it's gone through the majority of the pipeline, whereas the guy in the instruction decode stage is the later instruction. So obviously, if you want to, it's kind of like where it came together in the data hazard, right? This guy is going to get written to at some point. However, I'm reading from this guy, right? And I guess it comes into the case right here when I look at this T0 right here, right? In the case where I'm attempting to read from T0 and write to T0 at the same exact time here, the question now becomes, my behavior being correct is contingent on which one goes first. If the write back stage goes first, then, like first as in you could split up this cycle into two. If it's a stage where it's a write and then a read, then everything's good. Because this add I will write to T0, and then this add instruction will read the correct value of T0. However, if it's the case where I have a read and then a write, then things won't be as nice because the instruction decode stage here will be reading the T0 that has not been written back to yet by this guy. So double pumping is just a fancy way of saying, in the case where I'm reading and writing to the same register in the same cycle, which one goes first? So if we tell you assume double pumping, you could assume that the write will occur first. If we tell you cannot assume that, then you should just assume nothing. The read might actually occur first. Does that make sense? Well, hopefully it does. Got it, thanks. Oh, perfect. All right, lastly, we have control hazards. So control hazards is actually what you had to implement in your project 3. Give me a moment while I drink my tea. Oh, my throat. Okay. It's basically saying, if I have a jump instruction, or yeah, let's say I have a jump instruction. Okay, I'm gonna erase. Okay, I have a jump instruction. Jal RA loop. Okay, the question becomes, when is this executed? Well, I fetch the JAL here, I decode everything there. However, when do I actually figure out where I'm going to be branching to or jumping to? It's in the execute stage because it's what's getting computed by the ALU is the address that I care about. Address jumping to. Similar thing for a branch instruction. You're computing where you're going to go, and that's the guy that's coming all the way back here. You're computing where you're going to go at the end of the third stage. But what is the problem? While you're busy doing all this computation, what is in the instruction fetch and the decode phase? It's something else. Some other guy's here and some other guy's here. Whereas the JAL isn't here. So let's say hypothetically, the JAL is going to be taken. JAL's always taken. It's just an unconditional jump, right? So in the case of the JAL's taken, this guy I'm going to move to some other address. However, do I want to execute these two guys? No, I don't, right? If I have like JAL, RA loop, and I have an add here and a sub here, let's say loop lives all the way down here. Well, this guy will be in the execute stage, this guy will be in the instruction decode stage, and this guy will be in the instruction fetch stage. But I don't want to execute either of these guys. But the problem is they're already loaded into my data path. So you did this in your project, if you remember, you had to flush your pipeline, which means you need to override these guys with no ops to make sure they don't do anything. Okay, that's what a control hazard means. So for a jump, this always happens, and for a branch, this sometimes happens, right? Because in the case that a branch is taken, then you'll have a control hazard. But in the case the branch is not taken, then you will not have a control hazard. Like if I have a BQ x0 loop, that's in this case there is no hazard. Why? Or actually, in this case, there is a hazard. Why? Because I only figure out that this branch should be taken in the third stage, right? So therefore, these guys should get like x'd out, and they shouldn't be executed. However, if it's the case like where I've be any branch not equal to these guys, then there would be no hazard. Why? Because these guys are not equal. Um, branch not equal. Yeah. These guys are equal, so this guy will not branch, and I should execute these two guys. So no hazard necessary. Okay, so the question becomes, how do I solve this? How do we solve these control hazards? Well, one of them is what you did. You stalled, right? So stalling is the same as flushing the pipeline, which is the same as these no-ops. It basically means just wait. Okay, just wait until you know. So in this case, it's saying like if I want to solve this problem of like branching and jumping, just let the jow go to its third stage and just put in some no-ops for the first two stages. Then once jow figures out what it's going to do, then just continue executing. So don't waste your time putting anything into the first two stages. Flushing the pipeline, you basically did all of the stuff, right? It's basically saying wait, don't waste your time with these two instructions. There's actually another solution to this problem, and it's via something called a branch predictor. So a branch predictor is basically an extra piece of hardware that's actually smart enough to try to predict what you're going to do. Obviously, this only works on branch instructions, but it's saying it's a smart piece of logic. It's saying, look, depending on the design, it will try to guess which way you're going to branch. And there's a lot of complex knowledge done. It actually turns out there was if you remember like a few years ago, there were these like attacks on the Intel chips. Those actually had to do with the branch predictors. Or one of them, I think, had to do with the branch predictor. It was saying that a branch predictor, right, in some designs of branch predictors, what it actually does is it will actually have two concurrent states of your data path. One of them where the branch is taken and one of them where the branch is not taken. And what says is that once the branch is decided, then take whichever one of these two possibilities were correct and merge that with whatever's going on later and throw the other guy out. So the hack was that somebody was able to leverage the fact that they were both taken to execute some unwanted code. Point is, you don't have to worry about how branch predictors work. You can take 152 if you're actually curious. You'll delve a lot deeper into branch predictors there. But it's basically, branch predictors here. It's the solution. It basically solves the problem for you. It attempts to predict what your branch, whether you're going to take the branch or not. If it's correct, life is good. And honestly, most modern day branch predictors are correct. You can find ones that are like 99% correct. If it's correct, life is good, no hazard. But in the case that it's not correct, it'll just flush the pipeline just like you did in your project. You'll have to stall, pay the penalty for a few cycles, and then you can move on and continue with your life. All right. As a big picture thing, going back to the whole loop unrolling, I said earlier that the reason why you can't loop unroll forever has to do with the instruction cache. But the whole reason why loop unrolling works in the first place is because of this. If you unroll your loop more, you're actually minimizing the total number of branch instructions that you're taking to get back here. And the problem is that the more branch instructions you have, the more possibilities you have of encountering a control hazard, which stalls your pipeline. So if you can minimize the number of branch instructions that you take, then life is good. That's also why in some cases, some of you might have heard on your project that it might be a good idea to move function calls inside of it. That's because why? Well, function calls requires jumping or branching to a different part of your code. And these jumps and branches induce control hazards. Right, so it's not that big of a deal. Like you should obviously still modularize your code into different functions, but these are all things to keep in mind. And now you can understand why things get faster. All right, control hazards are a big deal, but we have these solutions: stalling and branch predicting. Yeah. All right. Actually, for experience, what time is it? 6:17. I can go through this. Yeah, I don't mind. Yeah. Okay. Sure. I'll go through it. Okay. So here we have 5 instructions. It says find all the hazards. Okay, so let's look here. So in this case, sub is utilizing T1. Okay, it's writing to it, and the next instruction, I'm attempting to read from the same guy. That is definitely a data hazard, and label that by a D. Definitely a data hazard. In this case, what's else happening? Is anybody else using T1? No, so we're good there. or is writing to S0. Is anybody else reading from S0? Yep, that guy right there. This is T1, it's a data hazard. S0, that's a data hazard. Is S0 used by anybody else? Nope. What about S1 right there? No, no future instructions using that guy. Yeah, seems like we're good there. So, seems that we have two data hazards. And then, in addition, we also have a control hazard right here. It's a control hazard, right? Because we have a branch instruction. Branch instructions induce control hazards. Branches and jumps, they always induce control hazards. All right. No. Let me check one thing real quick. Yeah. Cool. Yeah. All right. So let's see what we can. So what does it say? It says we actually cannot forward. Ah, perfect. And that's nice to know. So no forwarding means that we actually cannot solve many of these problems. So what it's saying is, well, let's look. T1 is not ready until this guy, right? But I need to use it here. So in a hypothetical situation, I should be able to forward it right there. However, I cannot do that because I'm not allowed to forward. So instead, what's the situation? All right, well, let's assume no forwarding, and let's also assume that there's no double pumping. Actually, let me see the assumption that we make on the worksheet. That way I can be consistent with what we write down. Oh, actually, you know what? It actually does assume that we can, okay, yeah, it actually assumes that we do have double pumping. So we'll assume that. Okay, so when is it ready? Well, T1 will be ready here. And then, yeah, so it'll be ready right there. So therefore, how many times do I need to stall it? I need to stall it twice, right? That way, in this case, IF will move there. So now this guy will no longer exist. If I stall it twice, then the new guy will be, IF will be there, ID will be here, execute, mem, right. And everybody else will also be shifted down by one. That's also something to keep in mind. Actually, I can write this out. So it'd be F, G, X, M, W. So if I stall this guy twice, therefore it would be like stall, stall, fetch, decode, execute, mem, write. And now we're good, right? Because now I can deal with T1 as I approach. If I have double pumping, then I will write to T1 here, and I will read from T1 there. So there you go. So two stalls. So two. All right. Now, in addition, let's look between 2 and 3. So 2 and 3 also have a hazard. So we can write, all right, so naively, it would go like this normally. Okay, what's the problem? Same thing. S0 is ready here. Okay, but I need it here. So therefore, I will stall it again. I will simply move my guy until they line up. Right there. So therefore, that will induce two more stalls. So there's a stall, there's a stall, there's a stall, there's a stall. Life is good. Yeah. And assuming that I can read and write in the same cycle, S0 will be ready here. And then I can read from it right there. And life will be good. All right, wonderful. Now we can look. So one thing is that some people might argue that there's actually a hazard between instructions 1 and 4, between the S0 or between instructions 2 and 4, between the S0 there and the S0 there. I guess you can read that as a data hazard. I wouldn't really view it as a data hazard, in my personal opinion. I think the solutions actually might consider a data hazard, and that's simply because it's obvious that regardless of anything, stalling, no stalling, forwarding, no forwarding, S0. Oh, actually, you know what? I'm totally wrong. This is a branch instruction. Duh. Yeah, this is a branch instruction. So therefore, there is a data hazard between these two guys because I'm attempting to read from S0 when I'm writing to it right there. So now let's look. Oh, also writing S's here is not the best thing. I just realized. I will call these S or no ops. Okay. All right, so now I have this data hazard between instructions 2 and 4 because I'm attempting to read from S0 maybe before I've even written to it. So let's write down. So the branch instruction would go here, F, D, X, M, W. I attempt to read from S0 here. right here, and I write S0 where? Right here. So I'm actually okay. So it turns out that given the fact that I've already stalled my pipeline this many times, by the time the branch gets there, S0 will actually already be good. So I could actually read at the decode stage, no problem whatsoever. So there's actually no additional stalls necessary for that one. All right, cool. Other than that, there's no other. Okay, I'm actually sure there's not so other data hazards. So lastly, we have to consider this control hazard right here. So we have the branch instruction. So I'll just like, since these guys don't, yeah. So I'll just say the branches right here. So BGEU will go FDXMW, and the add instructions here, right? So remember what we said earlier. In order to account for stalling of this branch instruction, what are my options? Oh, whoops. Well, let's assume we don't have a branch predictor. If we don't have a branch predictor, then I will actually need to stall my pipeline. Okay, so if I don't have a branch predictor, then I need to wait until this guy's done before I know what the deal is. So therefore, I'm going to have to stall twice. So originally, it was going to be this. But since I don't know what it is until the end of the execute stage, I should shift my guy by 2. Okay, this is assuming no predictor. Okay. Assuming that I do have a predictor, I actually shouldn't need any no-ops. That's the assumption that you can make. Assuming that we have a branch predictor that works correctly, you could assume that with good probability, it will actually give you the correct results. Therefore, you do not need to worry about any induced control hazards from here. So overall, with a predictor, I overall have 2 plus 2 plus 0 equals 4 stalls. And then without a predictor, I have 2 plus 2 plus an extra 2 equals a total of 6 stalls. Oh, excuse me. I'm so sorry. So yeah, let me double check my answer. Yeah. So that's the case. And that's how you should approach these kind of problems. You should write out these diagrams of like the FDXMW, kind of get everything lined up. Look at the assumptions that you make, forwarding, no forwarding, assuming can you read and write in the same cycle, is like double pumping enabled, all that kind of good stuff. And then from there, you should look at all the enumerations between all the different ones. And don't make dumb mistakes like me and ignore the ordering of things, right? The branch is actually reading from S0 even though it's like in the first position. So you should always look at like the forecast of like, oh, the S0 is there. If you remember earlier in a previous question, we said, look, in the worst possible case, like you don't have double pumping, nothing, you should look 3 instructions into the future and see all of these guys could possibly get a data hazard on them. If you do have double pumping affected, then only 2 of the ones in the future would get affected. So, yeah. All right. That's about it I have to say about this. Let's see if there's any questions. Just to make sure, so with a branch predictor, we assume there will be no control hazards, but there will still be control hazards for jump instructions. Yes. Yes. I'm pretty sure. I haven't taken 152, so like I'm not totally on top of how branch predictors work. It might be worth posting in Piazza to the TAs who have taken that class and who know more about branch predictors and how they work. I would also look at like previous exam questions. But I would personally say, and my word is not gospel, that if you have a branch predictor, it does not affect jump instructions whatsoever. Because there's no way to like predict the jump, right? Like you're gonna need to stall if you have a jump regardless. Let me convince myself that's true. If you have a jump, then the 2 are gonna get loaded in anyway. Yeah. There's no prediction to be done. Yeah, you're gonna jump regardless. So there will be a control hazard for a jump instruction regardless. If I'm wrong, please leave it as a follow-up on Piazza. That way I can learn. I'm always down to learn more about things I don't know. Okay, yeah, so that's all there is for today. Hopefully this was like comprehensive enough review of pipelining and hazards and all that kind of like timing diagrams and whatnot. I personally think your project 3 was like the most excellent review for understanding pipelining and all of this stuff. But I would recommend going over hazards questions simply because that was not tested on that was not really delved into in the project much. And like that actually has appeared in the past as just like test questions. So if you're worried about those kinds of test questions, it's great to review those kinds of things. Yeah, other than that, tomorrow will be the last stream. Yeah, I'll do parallelism. I'll kind of mash together MapReduce like Spark, data level parallelism, which is like SIMD, and thread level parallelism. Yeah, I'll probably put more emphasis on thread level parallelism than the other two. Just because the other two, I think, Spark, I think the discussion worksheet actually did a good job of going over Spark, and I don't think it's like conceptually too bad. And then SIMD, I think that last homework was an overexposure to SIMD concepts. So I think you'll be fine in that regard. And then threads, I think, are like actually a good topic. So yeah, thank you so much for watching. As always, for those of you who are watching this later, feel free to post all your questions in Piazza. I'd be happy to answer them. And good luck studying, everybody. Have a good night.